Welcome to Build Up, the European Commission's portal for energy efficiency and renewable energy in buildings. Directly stemming from the Energy Performance of Buildings Directive, Build Up is the meeting place for everyone involved in making the European building and construction sector more energy efficient. Every month we focus on a topic that is key to making Europe's buildings as energy efficient as possible. Exploring that, you can find the latest content such as expert talks, webinars, case studies and more. From architects and engineers to academics and policy makers, we've got you covered. Build Up brings together thousands of registered members to reap the benefit of Europe's collective intelligence on all aspects of energy efficiency and renewable energy in buildings. The Build Up portal benefits from the expertise of our ambassadors. Drawn from industry and academia, the ambassadors bridge the gap between EU and national level and help shape our editorial content. Want to promote your work? Build Up disseminates your research, projects and events through a variety of channels. Become a member to exchange knowledge with your peers. You can disseminate tools and resources, share good practices, and consult open source publications. Join the discussion on social media and become part of the Build Up community, or subscribe to our newsletter to receive the latest news. However you participate, the Build Up portal is here to inspire, inform and connect. Build Up, the European portal for energy efficiency and renewable energy in buildings. Join the community for opportunities and updates.
It is a pleasure for Build Up to host today's webinar and workshop event entitled Boosting the Deployment of Smart Energy Services in Buildings, Challenges, Opportunities and Barriers, brought to you by the domOS project partners and Build Up. This online workshop is split into three main parts, during which smart buildings experts from the industry and domOS project partners share their vision on smart buildings. Before we begin, we invite and encourage the audience to send their questions or comments to the speakers throughout the session. To do so, please use the GoToWebinar question function. These questions or comments will be addressed during the three podium discussions, one for each session of the webinar. Finally, we would like to inform you that you will be able to find the recording of this workshop on the Build Up portal and our YouTube channel in the coming days, together with the presentation slides. And now, without further hesitation, we will move directly to the welcome and introduction for today's event presented by Susanna Tatakova, Phoenix TNT. Susanna, the floor is yours.
Thank you very much. Hello, welcome ladies and gentlemen. Welcome to the final event of the domOS project. Today we are focusing on the topic of boosting the deployment of smart energy services in buildings. Throughout the afternoon, we'll explore the latest advancements, challenges, and opportunities in smart energy services. Our speakers, both from inside the project and from outside, will share insights and will lead discussions on key aspects of the domOS project and the topic itself. As mentioned, there are three sessions, each followed by a podium discussion where we will take your questions and discuss the topics. This event is a celebration of our collective efforts. It marks the successful conclusion of the domOS project. So let's seize this opportunity to propel smart energy deployment forward and shape a more sustainable future. I would like to show you the agenda. So we have the introduction. We have the first session followed by the 10-minute discussion. And then we will have two more sessions which again will be followed by the discussions. If you have any questions, please send them our way. If you are interested to get in closer contact, there will be contact information at the end as well. So let's kick off the presentations with Dominique Gabiou, the coordinator of the project, with the introduction to domOS. Enjoy.
Oh, Hello, ladies and gentlemen. I am Dominique Gabiou, professor at the Swiss University of Applied Sciences and also coordinator of the domOS project. Over the three last years, we had the opportunity to work with buildings, to work on the digitalization of buildings, and to try technology and services to make them more efficient and more flexible. And I will share with you some of the key issues that we learned during the project. Next slide, please. First, let me state that there will be no energy transition without the participation of buildings. You have here some figures from the European Union. Buildings consumed more than 40% of the energy in Europe. They generate more than 1/3 of the greenhouse gases. And within buildings, 80% of the energy is used for heating, cooling, and producing hot water. And well, what is the potential contribution of buildings to the energy transition? Three main contributions. First, buildings have to become more efficient. This is especially true for heating, cooling, and hot water, as this amount for the largest part of the energy consumption. Buildings have to be more flexible to adapt to stochastic new renewable energy, sun and wind, and also to avoid congestion on grid. And also buildings have to host local generation, mainly photovoltaic. Next slide, please. Of course, smartness and digitalization is not the whole solution to improve the performance of building. Regarding efficiency, of course, you can do a deep renovation, but with some smart services, you can get significant result in the shorter term and with less investment than compared to deep renovation. Building can also become more flexible. Flexibility means that we need some kind of conductor organizing local generation, consumption, and storage among the big consuming appliances and producers. And of course, regarding more local generation, this is not an issue for digitalization. But smart services for efficiency and smart service for flexibility are issues related to digitization. Next slide, please. So in the domOS project, we had two main axes. One relates to the development and prototyping and test of energy services for energy efficiency and for flexibility. I do not address these points as we have one session for each of these points. And the second part of the second axis of the domOS project is technology. Here, so the objective was to develop, prototype, and experiment what we called an ecosystem. It means an environment which streamlines the deployment of energy services and possibly other services in buildings. This will be also addressed in this session, interoperability in smart building. But let me say a few words already as an introduction to that topic. Next slide, please. our intention was to design an homogeneous information system for a building. To make it simple, what we have before the domOS era, we have individual appliances with their application or with their service. Typically, in a single family house, you may have a heat pump, a solar inverter, and an EV charger as independent systems, with each of the system having its own application. The intention of domOS for integrating everything is to have a kind of middle layer between services and appliances. And this middle layer would work like an operating system in a computer, meaning that services interact not directly with appliances, but with the operating system. And on the other side, appliances are not connected to the services themselves, but to the operating system also. Next slide. Well, what is the limitation of the silo approach? Basically two. First, there is bad user experience, as you have to deal with many applications. And also many services, imagine self-optimization of self-consumption, require the involvement of multiple appliances, and with a silo approach, this is not possible. Here you see an example of what we intend to do. We intend to make the smartphone revolution into building, to make it simple. Next slide. So what we did, we defined a mediation layer between the digital appliances and devices in building and application for energy efficiency, flexibility, prosumer information, and so on. And by doing this, the application would interact only with the middleware domOS layer, meaning that in the long term, we could have an app store where building owners and building operators could install application on their building and let it work directly and the application would have no idea about the underlying hardware. Like today, a computer program has no idea of the model of the printer when you want to print some document. So this terminates my presentation. Thank you for your attention, and I wish you a good webinar. So my presentation is finished. You can proceed.
So thank you for the word. Welcome to everybody. My name is Frédéric Reva. I'm professor at the HESSO and working on the domOS approach to make buildings smart. Next slide, please. Firstly, I would like to illustrate the kind of situation that we see in the real world. Next, please. Suppose that a building owner just acquired a solar panel for his roof. Next, please. To increase his own solar production, He would like to automatically charge his electric vehicle during daytime and prepare hot water for its heat pump. Next, please. By the way, some definitions. In domOS, all the devices that are fixed to the building and consume or produce energy are called appliances. And the fact to control appliances for some outcome, like charging EV during sunshine, is called a service. And services are automatically performed by applications. That being said, in our building, all appliances are connected to the internet, but are not compatible. Our customer has 3 applications on his smartphone. Next, please. 1 for each appliance, but they cannot communicate each other. This is what we call silos. This is the situation for end customer or building owners. This is exactly the kind of bad user experience that Dominique talked about in his presentation. Next, please. The value of domOS is to offer an intermediary layer between the services and the appliances present in a building, as shown in the figure in your right. The domOS inside layer breaks the silos to allow smart energy services to work across multiple appliances. The domOS approach is to take in account that there are legacy or existing appliances and IT infrastructure in a building, and that it is better to describe the world as it is instead of trying to change it. In the same idea, domOS is a specification that describes how to be domOS compatible and not a framework. This has many benefits. Firstly, the upgrade of platforms is easy and has the potential to be done on already existing platforms. Secondly, the work from manufacturers to adapt to domOS is light. They only need to describe their protocol, and in some cases, this can even be automated. This approach is also compatible with what the services need. Services need to support a maximum of appliances and be manufacturer agnostic. So if they can understand the description, it will work. Services also need to support many different building topologies. So if they can understand the description of the building, it will work. With a mix of different technologies that will be shown later, domOS allows any domOS compatible service to discover and understand what is present in a domOS compatible building and offers a uniform access to these appliances. Next, please. The domOS ecosystem is based on the following stack of components. Next, please. On the low level, domOS is based on the Web of Things World Wide Web standard. Web of Things allows to access appliances in a uniform way based on thing descriptions showing how to interact with the real world. But if Web of Things tell us how to interact, an application still doesn't know where to find these thing descriptions and what interactions are relevant. For this, we have added the other layer. Next, please. The second layer brings us models of appliances. Here we ensure that each type of appliance will have the same behavior. An application must see any heat pump as a heat pump, regardless of the manufacturer or the model. Next, please. The third layer is the domOS common ontology, which we call DCO. This is our common language. Here, we define the vocabulary used, the structure of the files, and what an application should look for. As ontologies allow it, we have developed this language with a strong link to other well-established ontologies like SAREF. Next, please. Finally, the fourth layer is a building description that has 2 roles. Firstly, this is the entry point for a building, like the index.html in a website. Secondly, it describes the building, the interaction, and appliances using the DCO. Next, please. Here we show how these components are arranged in an application use case. All buildings have a building description with its relevant metadata following the DCO. Next, please. The buildings contain also references to things descriptions that show how to interact with the real world. In domOS, each interaction is called MCP, that means measurement and control point. Next, please. An application that knows nothing on the building will query the building description to verify that the building has all the needed components so the application can operate. To understand the building description, the application will rely on the DCO. Next, please. Then, if the application can operate, it will call the things description to interact with the real world through the Web of Things. The DCO combined with the Web of Things ensures that any domOS compatible application has a uniform understanding and interaction model across all domOS compatible buildings. Next, please. We have modified the 4 participating platforms of the partners shown on right to be domOS compatible. Each participating building, that means dozens of buildings, has one building description following DCO guidelines. We have generated things description or models of things descriptions and linked them to the appliances. We have also updated our services to be domOS compatible so that they can work with the modified platforms. We have shown that a test service can work across all modified platforms. We were not able to try real services because of the 2 different use cases across the platforms. Unfortunately, it is not possible to test heating district services if we have an electricity optimization infrastructure. With these results, the bricks for interoperability have been demonstrated, and we want to make it available to the industrial world. Next, please. These results show that everything is now in place for adoption by the industrial world. We think there are 2 ways to do it. The first is to make domOS a standard, but it is not the purpose of the project. The second is to continue to develop the concept with industry actors, and this is the direction that we propose. We are working with industrial partners to implement domOS concept in their products. domOS offers the possibility to build manufacturer-agnostic applications for appliances, the same way smartphone applications are built for any smartphone. This opens the perspective of an app store for buildings based on domOS. This app store can be the vector of broad adoption for building energy services, which would help address the climate challenge that we have to carry on. So I have shown the domOS approach to interoperability, and it is time for me to give the word to the next speaker. Thank you very much for your attention.
Okay, thank you. Now it works. I'm Chris Broniman from Smart Grid Ready Interoperability Association. We are a non-profit organization that has 3 main targets in the mind. We create and support the bridge between flexibility technology generations. We don't invent the new wheel, we just make a bridge of existing standards that bridges technology generations. We harmonize this bridge with CENELEC, ISC, and ETSI, the 3 relevant bodies for interoperability and sustainability in telecommunication, and we create an international network supporting this initiative with joint activities. Please, next slide. It does not move on my control. We cascade energy managers software at any point. We name it communicator, and we connect that with products, that is real hardware, and enable a chain of software communicators on a DSO level, product that as a customer energy manager in the building, being a communicator to heat pumps, building wall boxes, PV inverter, and batteries. So our main focus is in the cellar of a building, dealing with flexibility. Next slide, please. A main target we supported and helped to develop was to create a generic flexibility indicator that shows the type of buildings or campuses the same way towards the grid. And this work was done together with CELEC, TC205 Working Group 18, and we named this interface S2 interface. It contains 5 bidirectional interface containers. Each of these control containers supports time setting, negotiation with the grid, and demand-side control. It uses 5 operation modes: operation mode control, direct control, then power sequence control, power envelope control, and fill rate control. This is all done in a similar way of control schemes, having timestamps, having a tool to negotiate with the grid side, but it is in this abstract, unique way. Next slide, please. This slide shows these modules being aligned to functional blocks of devices. These green blocks, they always show a specific function. Smart Grid Ready with the heat pump standard of Germany is a simple 4-stage control model: sleep, normal, little bit less, little bit more, going to as example a control for the power. It's not shown on this slide, sorry. Then let me take the domestic hot water control that offers you a fill rate control as example, that you can create flexibility with a heat pump. But everything is abstracted through this S2 interface towards the customer energy manager, showing it to the grid connection point. Next slide, please. To go a little deeper how Smart Grid Ready works, we create devices with functional profiles as shown before, and we create a machine readable interface description of, as example, a Modbus device. This machine readable external interface descriptions can be printed in PDFs, can be downloaded, and with our open source software code, we offer that in Java and Python. You can create automatically a device instance for accessing setters and getters for each data point. And we plan to combine that with domOS. domOS is also enabled to use our external interface description. Could you press the library Smart Grid Ready link, please? Yeah. You are now in our library. It's library.smartgridready.ch, and you see an example heat pump of Hoval. And if you could be so kind to only let data points being visible, and deselect the left buttons, the blue buttons, please. Little bit. Okay, we lose time. It does not work that way. Sorry, I have no control about the screen. So if you can scroll down a little bit, please. You can see these functional profiles, like a heat pump base module that has the main control of the heat pump, or the Modbus interface parameters, is it big endian, little endian, all the diversities of Modbus interfaces can be managed here, and the user of this external interface description does not need to know any information about Modbus. And we do that for the relevant legacy protocols and make that compatible with the IoT world in that way. Please, next slide. The work is not done with this S2 interface, so it needs to be brought to IEC. We did that in IEC System Committee 23K Working Group 3. And this S2 interface, this abstraction, is used by many organizations like KNX or grid system suppliers. And it will become an IEC standard within the next month. Of course, the whole thing is also coordinated with Senelec IEC, and in another European project, the interconnectivity project, is also a SAREF for Energy interface for the S2 interface. Next slide, please. Thank you. I just mentioned SAREF for Energy. It's a ontology that's created by ETSI. It's commanded by the European Commission, and they make tanks for appliances, for agriculture, for energy, for smart grid. And this smart grid part is connected through the S2 being listed in SAREF for Energy. And we can add plugins to this kind of listings to be part of the SAREF for Energy definition. The contractor is the European Commission, and the political consequence will be that SAREF will be part of the Code of Conduct for appliances, for smart appliances. Code of Conduct means that manufacturers will be motivated by labels to follow this Code of Conduct, and it's similar to the level A, B, C energy efficiency labels we support all over Europe, including Switzerland, of course. Smart Grid Ready plans to become a plugin for flexibility in this SAREF for Energy, and this may be a future project we could participate with the European Commission. That was the last slide. Sorry for the interruption with having no control, but somehow we managed to go through. Thank you.
Okay, hello everybody, and welcome to my presentation. In the few next minutes, I'm going to show you our approach of industrial deployment of smart services in small building. My name is Stefan Reh, and I am product manager by Vago in Switzerland. To begin, let me introduce you to the company Vago. Next slide, please. Vago is the worldwide leader specialized in electrical connection, electronics, and automation. The company was founded in 1951 and we have over 9,000 employees worldwide. We have more than 80 agencies, 29 subsidiaries, and 9 production sites. One of them is sitting in Switzerland, and it's why we collaborate with HESS Valley, the school where Dominique Gabiou and Frédéric Reva is coming. We work together in some innovation project. Next slide, please. We sell our product in many industrial sectors. As example, on the left-hand side, from the business unit interconnection, in control cabinet for machinery, on rolling stock material like train, but also in building with installation terminal blocks. Here you can have a look on a small terminal blocks. It's a product named 221, and the electrician can put the wire inside the connectors and wire the building appliances. From the business unit electronic, we have products like relay, power supply, electronic circuit breaker, or automation products are used in machinery as remote I/O, but also with PLCs and HMI in smart grid and building application. Last but not least, the business unit solution build a ready-to-use solution application like an EDM, an energy data monitoring. Next slide. Let's back to the subject of the presentation, the industrial development, deployment of smart services in smart building. Our project consists of developing an EMS, an energy management system, for single-family homes. Homes with PV production and large consumers such as a heat pump or the electrical vehicle charging station. The challenge is this kind of project is not technical complexity, but rather the numerous device variants. Their deployment on a large scale and the maintenance and installation fleet. If we think about thousands of buildings we want to manage, it's a real challenge we have. The main idea of the project is to use its own photovoltaic production to run the heat pump and recharge electrical cars. In short term, a self-consumption solution. Next slide. Our product vision. The project was launched with the vision to becoming a future provider of a service hosting platform for smart building and smart grid. In a first step, our target is to bring an MVP, a minimal viable product on the market that will increase self-consumption in small building. It's what you can see on the left side. In the future, we can imagine offering other services, and we have many ideas in our mind. You can find some of them ideas here on our road. Self-sufficiency application, EV load management, demand side flexibility application, etc., etc. Next slide. I'm going to be a little bit faster and suggest you to skip this slide. It shows the current status of our project, and you can comment on it later if you want. Next slide. To begin with, here's the topology of our solution. On the field level, you can find appliances like the heat pump. Here, as example, Stiebel Eltron heat pump, a PV inverter, as example of Fronius inverter, a Vago MID meter, or a charging station here, as example, a wall box from Zaptec. In the middle, these small pieces of hardware is a Vago CC100. This product acts as a edge device between the field and the external world. On the Vago controller, device drivers are running for all appliances lying on the field level. The Vago Linux controller is a single point of information for cloud application, cloud services, and local application, like dashboard or self-consumption algorithm, etc. The application can run locally or remotely on, as example, mobile file or mobile phone or smartphone, etc. The challenge here is how to handle the diversity of drivers for each pump, for each heat pump or charging station. You have different revision, and it's a challenge to manage all the revisions, the firmware version you have here. Next slide. To simplify and industrialize endpoint deployment, we develop a technology that use a common information base, the building system. It's the same idea as Frederick say or show in his presentation. Thanks to Docker, we are enabled to deploy specific containers for each type of appliances of device. You can have a look with the arrow that go to the right side. The building description is used not only to configure appliances, but also application, and that's the arrow that point in the left side. The use of building-specific data, like GPS coordinate, the number of rooms, the number of floors, are important data to customize the application for each customer needs. To summarize, the building description is a key to a successful large-scale deployment of building driver and customer application. I'm already at the end of my presentation. I was a little bit fast. Thank you for your attention, and I enjoy to answer your question during the Q&A session. Thank you.
Okay, thank you for all these presentations. If there is any questions from the listeners or the attendees of this webinar, please write them in the comments. We will read them to the presenters here. But for the time that you are writing these questions, I would ask a few questions myself. First, for Mr. Rivas, what can you provide us? Can you provide us an overview of domOS approach for making existing buildings smart? What are the key principles or methodologies that guide the process? You also mentioned that this could be done in an automatic manner. Can you just describe us a bit more how to make existing buildings smart?
Yes, thank you, Mattia, for the question. I think all turns around the building description and the thing description. You have to describe the building as with metadata, like it has been shown by Stéphane Rey for Vago, with the indication of the rooms, for example, or all the devices. And then you have to provide MCPs, measurement and control points, that describe how to interact with the real world. So I think this is one of the points that is the main the main apport of domOS to the project. Then it depends on your platform. If your platform has already some kind of HTTP connections to operate your different devices, it will be very, very easy to adapt it to domOS, because all the PCs are in places for the Web of Things. If you have very specific protocols, it will be just a little bit harder. But just go to Web of Things and you will see that Web of Things helps to find, has already solutions for different protocols. So maybe it will be also ready for you.
Okay, thank you. I have here one question to Stefan Ray. What kind of expertise will be required to deploy a WAGO solution in the buildings?
Thank you for the question. I think it's a very central point in our solution. And we want to address electrician with our solution. WAGO, as I show you, we are an electrician company. We sell some such small pieces of hardware, and our customer, our base customer, are electrician, and our target is to have an easy-to-use solution that the electrician can deploy himself. And our target is to have a simple as possible solution, and that's an electrician with a small training can be able to deploy a solution himself.
Thank you. I would have another question probably for Frederick. Is automation of services really what the customers want?
You have, I think it's not a question if the customer wants it. I think it will be mandatory in the future. We are arriving in some cases when we have dynamic pricing, when we have flexibility, when we have different kind of situations, that if you want to be effective, you should be always at home, always controlling your building, and this or have a concierge do it for you. And this is what we want to automate. We want to be very discreet in our approach, not trying to impose things, but I think it will come anyway.
Okay, thank you. And I have another question for Mr. Broniman. In the pursuit of making flexibility widely adopted with smart grids, what are some of the main challenges, and what are some of critical technologies or standards that the association focuses on promoting or developing?
The big challenge is that we have many protocols from IEC, SIM model, IEC 61850. Then we have DLMS and the COSEM models, and all these models are not really interoperable. And we try to create a bridge in between these relevant protocols. We don't develop a new wheel, but it's very challenging because the models are very different. And we also see that if we map that to SAREF, this is a huge work to build an ontology that matches the whole network. And SAREF is a matter of a political obligations. It's a mission given by the European Commission, and there are several universities working with, but having this mapped down to the target that you can connect with a data point. This is a challenge technology-wise, business model-wise, in between understanding of heads, between people that can interoperate in different thinking in different schemes. This is the challenge, and I believe it does not go that fast.
Okay, thank you. And we have time just for one more question. To Vago, what Vago will benefit from domOS project?
I think the benefit from the domOS project is to that we can develop our solution on an architecture, software and cloud architecture that will already improve, I think. And the experiences of the RHSS Ovalis in this project is very important for us, and to use an existing technology, and that we don't have the necessity to reinvent the wheel, as Christopher Brunniman say, is very important for us, I think. And we can reuse this technology, and I think our approach is to be open and not to invent a technology for our needs.
Okay, thank you. This would conclude the first session, as we are right on time for the second one, buildings and the electricity grid. I think the presenter already knows that they are who should be on. If any questions, some of them I see that they stayed unanswered are still to be asked. Please email them to domos@info. I will check what's the actual address, or ask the organizer to where the questions can be sent. Okay, thank you.
Hello, everybody. My name is August Beck. I'm from Green Power Denmark, the business association for green electricity producers and consumers in Denmark. I have a rather different subject for you today. I'm here to talk about the needs for flexibility in a security of supply perspective. As you all know, we are in a development stage in these years regarding how we produce our energy, how we consume our energy, and that's the things I'm going to talk to you about today. How are we gonna do this huge transition in the energy system and still remain our security of electricity supply? So I have to. Yes, exactly. Next slide. Yes, exactly. So the first thing I'm going to talk about is like these two main trends there is in the energy system, in the European energy system, which is also very true for the Danish energy system, which I'm a representative of. So the things I'm going to talk to you about today is in a Danish perspective, but would be relevant in a European perspective as well. So next slide, yes. First of all, one of these trends is that we're going to see an increase in fluctuating power production especially from wind and solar. There is a huge political willingness in member states and the EU for rapid expansion of wind and solar capacity, especially after the energy crisis as a result of the Russian invasion of Ukraine. We are going to see a very much expansion in the wind and solar production in Europe. So that's going to be an increase in fluctuating power production. NSUE calculates that in 2030, roughly 50% of our power production capacity is from either wind or solar. So in a weather-based power production system, it means that on a system level, we will have big variations in power production. And that's especially true in Denmark, and today almost 60% of our power production is from either wind or solar. So, and the other big trend is, and I'm not gonna tell all of you here today that we're gonna have a very much increase in the power demand, and that's especially for electrifying things that used to be based on the fossil fuels. So that's either for transportation, heat production with the heat pumps in households or in the district heatings as a supplement to get away from using Russian gas or fossil fuels, etc. We're also going to see an increase in power production for data centers, and in the European context, also hydrogen production with the sourced from wind and solar power production. So in a Danish context, the Green Power Denmark expects 3 times the electrical demand in the next 10 years. So we are going to see these two huge trends is that a much more higher part of our energy production is going to come from fluctuating weather-based energy, and that we're going to see a huge increase in power demand. So that begs the question: what about buildings? Because as some of you saw earlier, 40% of our power production or power energy consumption is used in buildings. So 40% is high number. So if you are going to do anything about flexibility, buildings is from a systemic point of view. We have to check the energy consumption in buildings and have to have means to control it, because from a system with a lot of power plants where we just manage the energy consumption or the energy production, we just turn the knob and manage the energy production. We are going to transform into a system where we have to manage energy consumption instead of energy production. So what happens if we doesn't do that? I'm gonna tell you about a analysis we did in the Green Power Denmark the last year. This is a shock scenario for the energy system. It represents a cold winter week with low wind and solar production in Europe. It's a rather complicated graph, so I'm going to explain it slowly to you. This represents a whole week in a situation in 2030 where we have a low production from wind and solar and high consumption, especially for heat in buildings. So the green ones in this graph is power production from either renewables such as wind and solar or biomass. There's gas turbines as well, and then we have the red curves, which is the power demand, the natural load and the resulting flexible load. So in a power system that's mainly with the fluctuating energy production and high demand, we will see problems in cold weeks, winter weeks in Denmark especially. So the bright red ones is called like it's unserved demand in the energy system. So our analysis and simulation shows that we will have problems having the amount of power that is demanded from the system. So this is just projections of the production and the demand in the European energy system, and then focused especially on Denmark. What happens in the security of supplies perspective if we turn the knob on the flexibility? Next slide. Yes. So this is a simulation of the same scenario, just if we turn on the flexibility. So this represents, first of all, you can see that there is less unserved demand in the energy system. The bright red ones chunks are decreasing, and that's a result of 10% extra flexibility from companies and industry. They've become more price flexible. 25% extra flexibility from data centers and their power consumption, and then vehicle-to-grid capabilities of 20% of each EV is capable of using vehicle-to-grid. So this shows that if you just turn in these simulations, turn the knob on flexibility, we will have a rather more secure supply of electricity in the system. So these are not the simulations of what happens if you do something with buildings, but whether what happens if you do something about flexibility, for example, in buildings and data centers and vehicle-to-grid. So this is an example of how flexibility also is a rather a fundamental component of security of electricity supply. So in a power system with increasing demand and fluctuating power production, we need to switch from managing power production to managing power consumption, and otherwise ends can't meet. That's it for me. I'm looking forward to the panel discussion later on.
Thank you. So I'm Olivier Geneste. I'm from Trilog. I'm chair of the data management working group of Bridge. I will explain what this is, but also involved in international standardization at IEC as convener of the System Committee Smart Energy General Group 3, and also involved in Flex community. I will talk about data standard and how this can support the integration of building into grids. Next slide. So first, why do we need to have this kind of cross-sector data action, meaning that we have the home and building sector, we have the energy sector and mobility transport. And in fact, we are seeing that there are more and more novel use cases that are appearing and services. And of course, it could be directly linked to the fact that we can use smart buildings and smart appliances to provide flexibility to the grid. And also when we are connecting to the mobility domain, we look at smart charging or vehicle to grid. In order to support this cross-sector data action, we don't need only a data model or ontology like we discuss very often about information level, but interpretability is required at many levels. We also need to have alignment of the functional processes for data actions, but also to align what are the roles, what are the governance, what is the regulation to enable several parties to exchange some data. And for that, we have a good collaboration between research and industry. And standards is one of ways to achieve that. So if you go to the next slide. So if we look at what we have in European research and innovation ecosystem, we see that there are many initiatives that started some years ago about data sharing and now going to data spaces. So if you go on the left side, you will see that we have this data-related project that was part of the Horizon 2020 program. And so there is Platoon or Interconnect, OneNet of BD4 Open and others, and they were all part of the cluster managed by a project called OpenDI, which is support action that covered not only the energy domain, but also industry, agriculture, and others. And on the other side, we have now some follow-up work that we went from this data exchange large-scale pilots to go into what we call the Common European Energy Data Space. So the idea behind that is that several parties from different sectors can share parties through a data space which defines some processes and some rules to enable people to exchange data based on common information models. So we see that we have 5 ongoing Common European Energy Data Space projects, and we have INCNet, which is support action that is managing the cluster of this project, and we see also data space project in other domains with the support of the data space support center. What is interesting is that Bridge is really transversal to that, and looking at the energy domain, we have been started in 2016, and we've been following many projects related to data exchange and interoperability. And also we have now about 100 active projects that we are gathering in order to provide contribution related to data management in particular. We see also we have other groups like Smart Grid Task Force, we have ATIPSNet, we have AAUTI, GaiaX, BDVA, IDSA for data spaces, and the data for energy working group that will come soon. And many reports have been published that will support the data interoperability based on standards. So if you go to the next slide. So if we look at one of the major results from Bridge in the past years, we have this data exchange reference architecture. So the main objective of this architecture is to support cross-sector data exchange. And in fact, the last version 3.0 was aligned with the data spaces context. In particular, you see on the left part, the local part, which can be locally positioned in order to support data exchange, to support digital twin and others. And the federated part on the right is more connected to how we can enable cross-sector data exchange and discover data from other parties, or how we can have the access rights to access them in order to build some new applications. So if you go to next slide. So besides that, we have other initiatives. One of them is FlexOffer. So it has already been mentioned by partners because it was used in domOS, but of course FlexOffer, which is this common generic core and possible application-specific profiles to support flexibility, is a way to represent that, and in fact has been used by more than 15 projects. So starting from Mirabel, and also TotalFlex, Fever, GoFlex, and now we have domOS and Gift and others. And so recently we created a FlexOffer user group, so it was maybe 1.5 years ago, with the objective to maintain the FlexOffer specification and promote the use of these specifications. We have currently 54 registered participants. It's part of the Flex community, and we already released the specification as open source, and really we are looking forward to get more and more people participating to contribute to the development of FlexOffer to make it an industrial reality. So if you go to next slide. When we look at standardization, we all know that there are many existing standards, and that it's sometimes hard to know where to go and what is relevant. So some time ago in 2017, a smart grid roadmap has been established. It's currently being updated, and so it's now freely available on the website that is written here from the iSystem Committee Smart Energy. The main idea is that you have a description of all the system, and subsystem by subsystem, you can click on it and you will have the list of available standards, also the list of coming standards that are under development. And you will have some SGAM diagram on which we are mapping the existing standards, so it can really help you to identify which standards are relevant and where you can use them. So finally, if you go to the next slide. So we see that there are many initiatives that are supporting the development of standard-based interoperable data exchanges. And all these initiatives are really complementary. So we have European Union Research and Innovation, in which we are doing some proof of concept and pilots. There are many industry alliances. You can see some name on the right that will enable to have this solution being field tested and to get some good feedback from real experience, and also to have a very short iterative loop, so we can get the feedback and really impact it to the specification very soon. And on the other side, we also have this standardization, which is very important as a slower mechanism, but enables to strengthen the industry adoption by making it a reference worldwide. We see that we already achieved several successes, and but it also gives us some future perspective. So we have this cross-sector use case are defined, and now we are demonstrating cross-sector integrated systems. We have some data model and ontologies, and now we want to achieve standards that enable semantic interoperability. We have this data exchange reference architecture, we have the data space, and this will lead to harmonized data exchange architecture and procedures. We are willing to leverage existing and future standards, and thanks to this smart energy roadmap, we know where to look at. And we also want to support industry adoption, and for that we have the user groups and we have the feedback loops that we can get from the industry and from the users of each of the technologies. So that was my presentation. Thank you.
So hello also from my side. I'm Mattia Arch. I come from a middle-sized company, INEA. Oops. Okay, so INEA is mostly automation, industry automation, and manufacturing intelligence-oriented company. But we have also a department for energy, which deals mostly with energy optimization of energy costs, and also European Commission research projects, which is where we are contributing with domOS. And I will talk about how to exploiting the flexibility of buildings. So what are flexibilities? Flexibility. Where can we get flexibility in a building? Basically, the main candidate for flexibility is any device that has storage capacity. So one of such examples is hot water boiler, which can store energy in a heat for quite some time, and it's not necessarily that electrical consumption happens when the heat consumption is required. Similarly, all the heating and cooling of the building is also the storage device, but in this case, the building itself acts as a storage, as a heat storage. Also, devices that cannot be used, that are not necessarily to be used at this point, they can be postponed. Those are also one type of flexibilities. Electrical vehicles, where we can say that the fully charged level should be reached at, I don't know, 6 o'clock in the morning. Battery or power walls are one of the obvious examples, and photovoltaics though it does not have the storage capacity, sometimes it could prove to be beneficial to just turn it off instead of inject this power to the grid. So now we know what are the where can we get flexibility, but to exploit it, we need to somehow we need some use case. So we can use it, of course, for price optimization, for cost optimization. In Slovenia, for example, we are in the middle of transitioning to a new tariff system where the tariff for transferring electrical energy will be changed multiple times per day. So one use case would be that this flexibility providing closed loads could be scheduled in the economically more optimal times of consumption. Some other use cases are frequency control, or voltage control and congestion management, which are mostly dictated or coordinated by either TSO or DSOs. But in these cases, usually much higher power is required from the actor participating for these services. But here comes into play aggregation, where we can use multiple of these flexible buildings to act as one on these markets or on these services. So also, next, we need to somehow connect this flexibility. We need to communicate with it, we need to measure it, we need to control it. And here comes the domOS solution really handy. It simplifies a lot the integration of such assets. One thing to consider is the individual building flexibility is really not that big, and the IoT devices that are used for this should be as cost effective as possible. So it's now that we have monitoring and controlling of flexible devices, we also need to somehow orchestrate them. These control devices are sending measurements to an agent, to a flexibility agent, and combined with user settings, they generate flexibility offers. These flex offers were also already mentioned a few times today. Multiple of these flex offers are gathering in an aggregation platform. And on the other side, the grid also provides its own flex offer, but with the main difference that it's not offering flexibility, but it's asking for it. And then after this, the optimization algorithm tries to find optimal solution for this, and based on this solution, the control devices are the devices are controlled to extract the flexibility from them. In these schedules, so-called schedules, are delivered to individual control of the device. They are monitored and measured during the activation, and after the flexibility, after end of flexibility requirement required period, it's estimated how much of flexibility was provided. So to sum up, we need to identify flexible devices. We need to somehow connect them to an aggregation platform where it can match with other types, with counterparts of flexibility requirements. And then we need to trigger or control these devices to extract the flexibility from them. That was it from my side. And since I'm already also chairing this podium discussion, I will just stay online and ask for the other two presenters to join me on camera. Hello.
Hello.
Is Oliver still here?
Yes, I'm here.
Yes, okay, perfect. So while we're waiting for questions that will come from the attendees, I prepared some questions of my own. First, for Mr. Bech, what are some key future features or technologies that enable buildings to become intelligent in terms of energy management and optimizations? So the main focus, of course, being that we will be able to adapt consumption to production, or to make this transition to control consumption.
So the question is, which technologies will be the main? Yeah. Okay. I can speak from a Danish perspective and from a systematic view for the energy system as a whole. In a Danish context, we will expect that 1.5 million EVs is going to join the roads in 2030. The flexibility in the Danish context will mainly be from vehicle to grid capabilities. So, and not mainly, but I'll expect a lot of the flexibility coming from the vehicle to grid capabilities. And then from district heating, we have a huge district heating system in Denmark, and a lot of district heating connections, especially in the big cities. We will have a lot of flexibility from that, and the energy consumption from these power plants is gonna be higher, and then we will have later on a presentation from Aalborg, which has plans to have a huge heat pump, which I will expect will have a lot of capabilities doing flexible consumption. So my expectation is, especially from vehicle to grid capabilities, district heating flexibility, and we will have because of price variations in because of the wind and solar power production, we will have a lot of flexibility in data centers and power to production of hydrogen. There will be a lot of flexibility from that as well.
Okay, thank you. And I have one question for Mr. Genest. What are some key considerations or best practices that building owners and operators should keep in mind when implementing data standards to support grid integration? How they can ensure that their system will be compatible, or that will be compatible and interoperable?
So indeed, that's a challenge because there are many existing standards and solutions. And currently, it is sure that we cannot replace all the standards by one. I mean, every time we try to do that, we just add one new standard. So that's why what we are currently trying to define with data spaces or other initiative based on ontology is to see how these tools like ontologies can be used as a kind of proxy, meaning that you will be able to map your own existing data model or solution from any manufacturer to this common reference, and then it will allow you to exchange data with other sector and other parties without changing what you have on your side. So that's what was developed in particular in Interconnect project, in which we have many smart appliances manufacturer, we have white goods, we have also smart building and everything, and there are really some different roles that we did not try to align, but we listed for each of them what kind of data could be useful for others, and we did the mapping so that this data can, in this specific case, be provided in a format that can be understood by others. And that's probably the key for cross-sector data exchange.
Okay, thank you. And I have one question. I don't see for who, but we'll figure it out. How do we get products that offer demand flexibility into the market if the TSO and this DSO refuse to provide initiatives for the end users? Do we need to be more involved in the politics?
In Denmark, we are about to implement something called independent aggregators, which is probably going to be a supplement, especially for the TSO, DSO problems, as how big do you have to be a actor on the energy markets? In the current regulatory framework, you have to be a big player to do these balances in the energy system. With these independent aggregators, you are able to, with intelligent operating systems, control and aggregate a lot of, example, EVs in the power circuits, and so you can balance the energy system. And these independent aggregators is going to be a huge deal moving forward. Yeah.
Okay, thank you. I have another question which I can partially answer, I guess. How to reward flexible buildings? It's quite hard because it at least in Slovenia or in most of the Europe, the flexible power or energy does not have yet established market. But there are some cases that this energy activation or flexible energy activation is being paid if the prosumer is being included in a group of prosumers that is participating in system in ancillary services. For example, tertiary reserve, which is typically a frequency control service. But since all the powers from buildings or domestic users are relatively small, these rewards are quite small. So would you to add anything to this?
That's the case of the independent aggregators, exactly. So yeah, the rewards are not very high at the moment, but my expectation, or Green Party's expectation, is that if we turn the energy production into more fluctuating, weather-based energy production, the variations are going to be so high, and the need for ancillary services and the needs for balancing the system is gonna make it a better business case in the future. Especially, yeah, from moving from managing power production to managing energy power consumption. So I think it's going to be, for now it's not profitable, but in the future it probably will be.
Maybe a final word from you, Oliver.
I mean, like regarding this flexibility, of course, we need to take in mind that we have several levels, and sometimes the reward, which may not be economic, is only at local level, because we know that, okay, we are improving our self-consumption, or we have other objective. It can be at a district level, meaning that we are sharing with other parties the goal to maximize the areas production places. So of course, it can go to the market. And based on what you mentioned earlier, of course, market can be the one from the grid operator, of course, but it can also be for the BRP for portfolio optimization. And of course, it could be through the energy suppliers via implicit demand response. And in this case, it would be tariff-based. But for sure, it's a mix of everything. And depending on the use case, we have different rewards at the end.
Okay, thank you. This would conclude this second session, as it's almost time for the third session. I would once again repeat that the questions that you might have and you didn't write in the comments, you can send them to the email info@domos-project.eu. You can see it up there in my camera. And now I would invite you all to listen to the third session, increasing energy efficiency through smart services. I think the next presenter already knows who he is, so thank you.
Yes, I think it should be me. My name is Felix Bünning. I'm the CEO and one of the co-founders of Weibu. Weibu is a Swiss startup from ETH Zurich and EMPA. And what we're doing is self-learning predictive control for light commercial buildings, and how exactly that works, I'm going to show you in the next slides. All right, there we are. So at Weibu, we are building a cloud platform to empower building efficiency. What that means precisely is that we connect to so-called smart thermostats. So smart thermostats are little devices that either control your radiator or your floor heating system and replace the normal kind of the manual turning thermostat. The difference to a normal thermostat is that they send their data to the internet. So we are able to connect our cloud to these devices, read measurement data from these devices, process the data in our cloud and send back optimized control signals. How exactly that works, I'm going to show you on the next slide. But under the line, we are able to reduce the energy consumption of a building by 20 to 40%, while even increasing the comfort in these buildings. Our technology is based on 5 years of research at ETH Zurich and EMPA. We are currently undergoing certification by South Pole, and we have collaborations with the market leaders in this smart thermostat area. So what is under the hood there exactly is what we call self-learning predictive control. And this is how it works. So we equip a building with these smart thermostats. From the smart thermostats, we read sensor data. So this is valve openings, which is basically a proxy for how much hot water is flowing through the radiator or through the floor heating system. Then we also collect room temperatures, and we combine this with the weather forecast. So ambient temperature and global solar irradiation. When we equip a building, we first have a measurement phase, kind of where we collect data, but then based on this data, we learn the thermal behavior of each individual room in a building with methods that combine machine learning, but also physical principles. And once we have these models, we can use these models in the so-called predictive control algorithm. That basically means that every couple of minutes we take in the weather forecast. The models show us how the room temperature in each individual room in the building is going to evolve in the next couple of hours. And then we can optimize how much heat we put into each individual room in the building. And this has two main advantages. You can run super aggressive night setbacks, for example, because the algorithm knows for each individual room when it needs to start heating in the morning or during the night again, in order to be at the comfort temperature and time. And you can anticipate solar gains, which basically allows you to use the sun as a free heat source with this controller. So I've brought two examples of buildings where we got these algorithms into work. So in this building here, we replaced 140 thermostats with smart thermostats, coupled them to our cloud platform. And in this building, it's now running for the third year. We are saving 30% of energy, while actually most occupants claim that their comfort improved or stayed the same. So in this building, we save about 6,000 francs of heating costs per year, while charging subscription costs of about 1,800 francs. So 2/3 of the savings stay with the operator of the building. This is another example we equipped last year. Here we're saving 27% of energy, and one big advantage of our technology to other retrofit methods is basically that the building is operational again in the minute where you switch the manual thermostat against the smart thermostat, so you don't have any downtime of your building. So how do we sell these projects or the technology? We basically offer end-to-end projects. So together with the customer, we are selecting the building, we organize the purchase of the hardware, we organize the installation, we even have our own installers that sometimes do smaller buildings, or we work together with our partners. Then we connect the thermostats in the building to our cloud, and 1 to 2 weeks later, after our algorithm has learned the thermal behavior of the building, the customer basically saves energy. So these are our advantages, or the advantages of our technology on one slide. So basically what you get as the end customer is 20 to 40% savings in your building, while even improving the comfort. But our technology also allows to give you extended reporting. So we can do reports of already achieved and future energy savings, and also give the facility management maintenance suggestions. So with the data that we have in our algorithms, we can, for example, analyze whether the hydronic balance is correct in a building, or if there's something wrong with the supply temperature, and many other features. We are also ready for the future, and what that means, I try to touch a bit on my last slide here. So we've heard a lot about flexibility and flexible buildings already in the presentations before. We can use our technology to do exactly that, provide flexibility with buildings to the grid without hurting the comfort in the building, because we exactly understand the thermal behavior of the buildings. So with our technology, we can basically maximize the flexibility while keeping the comfort, because our models know exactly how much flexibility can I offer in order for the comfort to stay in a certain range that we can define, or that the customer can define. So with that, I think I'm in time. I'm already at the end of my presentation. I'm looking forward to the discussion at the end. Thank you. There are 4 backup slides, so maybe just skip through them. Yep, thanks.
Henry, sorry, unmute your micro, please.
Yes, I heard I was muted, but I was not able to unmute. Now it works. Sorry.
Okay, there you go. Great.
I'll start again. My name is Henrik Stermose. I am CEO and co-founder of NeoGrid Technologies, founded back in 2010. We engage in intelligent and database energy control of buildings' heat consumption with the aim of reducing energy waste in buildings. We are currently operating in plus 800 light commercial buildings, and we are a team of 17 people located in Aalborg. During the past 3 years, we have been participating in the domOS project, extending our services toward building managers and district heating operators. In our short pitch here, I will start by briefly focusing on the services we provide from NeoGrid, focusing inside the building and how building in the context of the surrounding distribution system can play a vital role of minimizing the all required energy in time and space. The result achieved in the district heating level will be presented by Christian Bjørsen from Aalborg Forsyning right after here. Let's see if I am able to shift the slide. I am. Optimal control of strategies of heating in buildings is more or less like a game of chess with many different strategies and outcomes, which can be hard to handle for the people or the human mind. Our technology replaces standard heating curves and other rule-based logic today controlling the production of heat in buildings with database cyber-physical models and machine learning solution delivering optimal decisions at all time. We are approaching the building from outside and in, providing optimal control of the forward temperature from the central district heating mixing loop in the basement, typical of buildings. And then we are operating based on the forecasted energy demand of the building. As an add-on to that, we can offer optimal control of smart radiator thermostats and control of the apartments at room-based level. That is pretty much the same as the previous speaker. But our approach here is mainly on the forward temperature in the building. Our primary segment is the social housing sector, but we also provide services from the muni-P sector, whatever, institutions, schools, and kindergartens. We also focused on complex building, and that's building where we have ventilation system, cooling, playing together with room heating. And our focus here is deliver the optimal indoor climate at lowest cost. Yes, it worked. Via data, we learn how building consume energy. We're doing that by measuring the amount of energy delivered to the building, the indoor temperature in the building that the energy translates into. Then we are having the outdoor weather of the building. And then we train a thermodynamic model of the building in order to see how the building consumes energy. If we then have a weather forecast for the next 24 hours, 38 hours, whatever, we can then forecast how much energy we need to put into the building and which time in order to achieve the desired indoor temperature. Compared to standard heating curve controllers, this approach here has superior results. For a given building, we constantly document the performance of our controller. Compared to a baseline, without our control, our service provide energy savings in the range of 15%. On top of that, we provide a number of KPIs regarding how the building is operated and how it's performing, but also with a focus on the cooling and the return temperature of the district heating system, which is important for the district heating companies. And what you can see here, like 15% of savings. On top of that, we deliver a number of services for the building, the tenants, and indirectly also the district heating company, with the aim of having the lowest possible flow temperatures in the building and then reducing the heating cost. We are an add-on to the existing building equipment, the BMS controllers or other kind of controllers. That means that we reuse as much as possible in order to lower the installation cost. Typically, we obtain savings, as I mentioned, that's typically between 10 to 20%. We typically see 5-degree lower return temperature from the building back to the district heating network. And our installation in total have a return on invest on 2 to 3 years. Within the domOS project, we extended our service with the district heating towards district heating companies, adding a local mixing loop supplying a cluster of buildings. Transmission temperatures were dynamically controlled and lowered from 80 degrees to 55 degrees centigrade, minimizing the distribution circulation loss, and the aim also to investigate how buildings were performing in the future low temperature district heating system. I will now switch to Christian, who will take this to the next level.
Yeah, I hope you can hear me, and hopefully I'll be able to control the screen. Let's see. As Henrik just mentioned, I'll shortly tell a bit about the results from this domOS project that we work with. All in all, you can see here what it's meant for the buildings at Fyrkilevej, where we put in the mixing loop in the district heating system. The supply temperature was reduced from around 82 degrees and down to around 55 to 60 degrees, with the energy demand being or the comfort of the building was above the same. As you can see here, also you can see a trend of the energy demand was lower inside the mixing loop than it was outside the mixing loop. So for the tenants, what did it mean for them? They had a decrease in the energy consumption and experienced a lower tariff for the district heating system. For us as a district heating system or district heating supplier, we experienced this lower in the supply temperature, which also led to the decrease in the energy demand. It increases the lifetime of our service pipes, and it's really optimal for the green transition, where we need to change from fossil fuels to renewable energy, where we look into a more electrified district heating production. If we look into what does it mean for us as a district heating supplier, just with reducing the temperature, we experienced that in this area with around 500 meters of pipes and service pipes, we could reduce heat loss, net loss from our district heating system with around 20% when reducing from 80 to 60 degrees. If you look to or extrapolate this result to the entire grid, we can look into that for each degree that we can reduce the supply temperature, we actually reduce the heat loss of our system by 1.1%. So just by be able to lower the supply temperature by 1 degree, we can save a bit more than 3 gigawatt hours. And of course, you can see if we lower it by 2 degrees, we can save double this amount. So why or how are we able to do this? Looking into the future, how can we use the flexibility in our district heating system? We look into how to make the smart production, make the smart grid, and the smart buildings, where to integrate these, where do we have the coherent places where we can find something that's beneficial for both the consumer, for the buildings, and us as a utility. Today, right now, we experience the energy savings. We have remote meters, remote read meters. We know what our consumers use by every hour. We rent out district heating units. So tomorrow, or just in the next day, as Henrik told, we can be able to remote control these units. We can use AI to figure out how to control the units. We will be able to integrate the building and the building designs into the distribution system, into our district heating system, and we'll look into delivering comfort instead of delivering or selling kilowatt hours and selling hot water. So someone asked about how we can reward this flexibility in the system. This is probably some years ahead, but when we look to the district heating system being 100% renewable and electrified with lower temperature, we look into the possibilities, or thinking about the possibilities of time shift the consumption at our consumers. And the initiative to do this could either be when the district heating is green, or differentiate the prices by the hour, so that the consumer can be able to move the consumption from one time to another, where we will be able to move the peaks from maybe in the morning to the daytime, and in the evening to the later in the evening, or another time where it's cheaper for the consumer to use the energy, like when you use electricity, that it's that the temperature, the price is differentiated by the hour. Very shortly, how do we do this, and how we'll be able to do this? How do we integrate it into our products? At the moment, we rent out district heating units, and if we can send out a signal to the district heating units, or to a signal to a company like NeoGrid, being able to, for instance, time shift the consumption from 6 to 9, where people take a shower, close the radiators, and move that consumption to before and after, we can peak shave the consumption, and in that way being able to remove some of the peaks. And the peaks for us is very expensive, both to supply and also to build these production sites that should be able to supply this these peak demands. This is everything from me, and I'll give the word to Yves, I think, who will have the last presentation.
Right. So good afternoon. So my name is Yves. I work for CSCM in Switzerland, and I'm an R&D engineer. What we have done in domOS is called energy efficient heat generation and distribution, and it's actually very much linked to what was presented by Vibo in the first talk, and then later by NeoGrid. So it's a very similar approach in the sense that we try to retrofit the heating curve. So I clicked, but nothing happened. Okay. So what is the objective of this closed loop energy efficiency service? So to understand what we do first, how does a normal heating system work? So here it's a case of a gas boiler, but the same applies for heat pumps or district heating. It's generally controlled by the outdoor temperature, so by the means of a heating curve. And at commissioning, usually the technicians will make sure that people are happy in terms of comfort. So the fluid will be in general too warm, to make sure that people don't complain. That results in higher energy bills, which people complain about, but they have to live with it because they don't have the hand on that. What we want to do is reduce the heating costs while maintaining comfort. So we still want to see happy faces close to the radiators. To do that, we rely on smart thermostatic valves. So it's the kind of elements you see here. to actually understand what happens at radiator level. So basically, we try to compute how much energy is required at the radiator, and then knowing that information, we can steer the heat generation in a better way. And that's really how we can maintain happy people in the rooms, so smiley faces, and use slightly less energy. In domOS, where did we test that? So it's a test site in Neuchâtel, and here I will try to make a link between what I've shown before and the way the test site looks like. So it is equipped with one big gas boiler, so to generate the heat. And then the interesting feature, it has 3 independent heating circuits, which allow us to actually compute 3. It's as if there were 3 buildings connected. That's the bottom line, which makes our test case way more interesting because we get 3 buildings for the price of 1. And all that feeds around 70 radiators. So it's a quite big building that has 7 flats plus some commercial areas on the ground floor. And as I mentioned, there is one big heat generator for 3 heating circuits. So we actually compute set points or values to be applied at the heating circuits. And then the gas boiler actually adapts or lives its life as it should to satisfy the needs of the heating circuits here. What are we using to do that? So most important, the smart thermostatic valves. So here we started with these. They are from the brand Hora. Then we moved to another one, which is the Viki, that have the advantage to talk over another network that don't require us to add these gateways, which are not always convenient. So we can actually now live without this. This information then goes to CSCM, where we do the math and then send it back to the gas boiler via this. So in that case, we had to install a small gateway to actually talk to the gas boiler. And here, that's just a small print to show that we can actually send commands to the gas boiler and it reacts as it should. So that's always a good sanity check to make sure that we can actually do what we want. Then, what did we learn during the project? So these are results that we generated during the 21-22 heating season. And all the plots that I show have the same logic. So on the bottom axis here, you see the average outdoor temperature over 1 day. So each point is 1 day. The red is the baseline, so that would be operation as usual. And then the blue line is our domOS solution, or in that case, the closed loop energy efficiency. Here we see the supply temperature that would go to the radiators, and we see that for riser number for the heating circuit number 3, it was decreased on average by 5 degrees quite consistently, and people were still happy. So I put it as green, we were happy, that's what we expected. Then if I move closer to the radiator, we can see that this time here it's not temperature that I show, but it's the average valve opening for a flat, or for actually all the flats connected to that loop. And you can see that the opening of the valve went from like 40-something% on average to 65. That's also something that we wanted to see, because since the fluid is less warm, the valve needs to be more open to actually throughput the same amount of heat and keep people happy inside. Then the last thing we saw is that the energy at riser level was equal for the 2 of the risers, which is also not surprising, since at the end of the day, people still need the same amount of heat to be happy. It's just that our motto is that we can drive at a lower temperature, so we have a better efficiency at generation. The good thing is that on the riser number 3, we even had a decrease really of net energy of around 13%. I put it as not expected, because again, the energy should be the same, but actually the insulation around the pipe was that bad in that case that probably by lowering the temperature, we drastically reduced the losses in the piping, which probably explain why we had this, I would say, unexpected saving on this riser here. So from this, I can already conclude, okay, deploying is really fast. So changing these valves takes literally less than a minute once you know how to do it. The way the algorithm operates is exactly what we want to see, meaning lower temperature at the riser level, and the comfort is not impacted. So both, we didn't get any complaints, and also if we check like quantitatively, we don't see a reduction of the measured temperature in the room. So we were very happy with that. So we submitted a patent, so it's still ongoing. We're now doing this ping pong where the reviewer says, please check this, check that. And it looks, I would say, rather positive so far. And now comes the but. Normally with the good results I've shown before, I should say, great, we saved 15% of primary energy. So unfortunately, I cannot say that. And we had to investigate quite a lot. It's actually the heat generator that building is so oversized that even though the temperature is lower on the riser, the heat generation is still producing energy that is way too, or temperature that is too high, because it turns on like few minutes, turns off, and it has this very erratic behavior, and it's ridiculously oversized. So that is, I would say, the downside of what we learned in that test site. The good news is that we now have tests that are going on in one of the building of NeoGrid with a heat pump, and that looks way more positive in the sense that there we see what we actually wanted to see also in terms of primary energy. And that was my last slide. Thank you very much for attention, and I think it's time for the podium discussion.
That is correct. Thank you. Yes, I would ask Christian, Henrik, and Felix to join. We had some questions already arriving during the discussions, and we are running a bit late, so it will be time for just one question for each. How much, for Felix, how much data is required for your model? Is your model trained on room level or building level? And do you account for heat transfer between rooms? That's the question.
I mean, some of these are secrets, but so we train on a room level, and we require just 1 or 2 weeks of data. I think that's actually one of our maybe not USPs, but if you look at a lot of other companies that do predictive control in buildings, they look rather at 4 weeks to even 3 or 4 months. We require relatively low amount of data because I just quickly said it, we kind of combine machine learning methods with some physical principles. So our models know even before they see data that heat, for example, goes from hot to cold and not the other way around. Solar irradiation always causes temperature increase and never temperature decrease. And if you find a way to kind of implement physical principles in machine learning methods, you can save a lot of, or you can increase the sample efficiency by quite a bit.
Okay, thank you. There was a comment for Henrik and Christian, nice results, with a question, what are the barriers preventing large-scale rollout?
Seen from my perspective, there's at least no technical barriers for the large-scale rollout. What we face when we are selling our part of the product is that, well, it's too good to be true, therefore we don't trust it. So that is, it's a human barrier. But anyway, over time, and that's not a lot of time, but we need to invest that time, is that, well, it is overcome and then it is possible. But that is, I think, the main barrier.
From our side, I think the main barrier is probably the lack of different kind of or different temperature zones in our distribution system. So being able to reduce the supply temperature in some areas, we need to be able to have different temperature zones and different mixing loops in respect to different places in the city. And that's probably one of the biggest barriers. Of course, we know from all the meters, around 50,000 meters that we have, which buildings we have a problem or which buildings have a problem in a low temperature. But I think the main barriers for us is the lack of temperature zones.
Okay, thank you. And one for Yves. What are some of the main challenges or sources of inefficiencies in building heating system? Did you find out? I know that you found that the boiler is really oversized, and the insulation of the pipes is bad. Did you find out any other inefficiencies in the heating system?
So in general, it's really bad commissioning. It boils down to that. I mean, people, when they set it up, they do it in a way that users don't complain, so that they have way too warm all the time, because people complain when they're cold. And then what can also happen is that tenants try to goof around with the controller, and then it can go to God knows what. But yeah, I would say bad setup.
Okay, thank you. As I mentioned, we are running a bit late. This was it from my side and from the presenters, and I will give word to Susanna, and she will make the final words. Thank you.
Thank you, Mattia, and thank you to all the speakers for their presentations and their discussions. I would like to thank BuildUp for co-organizing our final event. And of course, I would like to thank all the attendees for their questions. If you have any follow-up questions, you can use the info email, which is listed on the slide you can see here, and you can visit the website of the project. One more announcement for the end: we have released the final video of the project, and you can find it on the website as well. So go and have a look and learn more about the project. Please follow us. There will be some more following information on the website and on our social media. So I'm giving the word back to BuildUp. Thank you so much.
Thank you to you, Susanna. It has been a real pleasure to have you and all the speakers, and for such an insightful share of the domOS results with a lot of relevant data coming from the demonstration sites. We have already give to our audience your mail, so they can have further information if they need it. Thank you to the audience for attending today's webinar. A reminder that you will be able to find all the recording of today's sessions on the BuildUp portal and our YouTube channel in the coming days, together with the presentation slides. BuildUp has a number of webinar sessions also already in the pipeline for the rest of February and also for March. So keep an eye on the BuildUp calendar of events and our social media for update on this. Be sure to check up the BuildUp website and follow us on social media for updates. We wish you all a very pleasant end of your week. Thank you and goodbye.